Hello, everyone. Thank you for your interest in our work. Our team is from Harbin Institute of Technology, National University of Singapore, Fudan University, and Wuhan University. In this work, we are the first in the community to propose the new task of multimodal universal information extraction. Our paper, Recognizing Everything from All Modalities at Once, Grounded Multimodal Universal Information Extraction, has been accepted at ACL 2024 findings. Information extraction, aka IE, is one of the long-standing core topics of NLP, encompassing subtasks such as named entity recognition, relation extraction, and event extraction. Research in IE has evolved from focusing solely on textual data to embracing various other modalities, leading to the development of multimodal IE, like images, videos, and audio. Despite the growing research efforts dedicated to MIE, the exploration in this area remains insufficiently developed. We argue that some key aspects must be fully considered for future MIE research trends. Firstly, current studies primarily investigate MIE tasks within individual modalities or certain modality combinations. With the existence of several modality categories and diverse definitions for different IE tasks, studying each modality separately to construct specialized MIE models would inevitably lead to resource wastage and inefficiency. In real-world applications, there is a constant need for building unified systems with one-for-all, robust generalizability for faster practical deployment. In light of the recent success of textual universal IE, MIE unification should also be promising. Second, the majority of existing studies exhibit a bias toward text-centric IE outputs, necessitating the decoding of detailed textual IE labels and inherently prioritizing text. While they often treat other modalities as auxiliaries and do not produce outputs for them, this practice does not align with reality because all modalities can equally carry important information. For example, even infants who have not yet learned to speak can learn about entities from vision. Thus, each modality should be treated equally and detect fine-grained information from all given modalities. Lastly, most current MIE involving multiple modalities, e.g., image and text, tends to extract the modality-aligned part of the information under the assumption that different modalities associate with each other. However, in practical scenarios, the information carried by different modalities can be either shared or unrelated. This suggests that information should be flexibly recognized from any modality sources. So, in response to these challenges, this paper is dedicated to pioneering a novel task, grounded multimodal universal information extraction, aka MUIE. As illustrated in this figure, MUIE aims to unify the modeling of various IE tasks with any, or combination, inputs across the most common modalities, e.g. text, audio, image, and video, and produce fine-grained multimodally grounded IE results, which covers grounded NER, RE, and EE tasks. To solve MUI, we consider taking advantage of the existing generative LLMs with in-context instructions. We develop a novel multimodal LLM, ReIMO, achieving recognizing everything from all modalities at once. ReIMO not only outputs all possible textual IE labels, but also identifies corresponding groundings across other modalities. One, statically, by segmenting visual objects and audio speeches, and two, dynamically, by tracking textual or vocal events in videos. Technically, ReIMO utilizes ImageBind as a multimodal encoder to project image, video, and audio inputs into LLM understandable signals, and employs a Vicuna LLM as its core semantic reasoner. At the decoding end, we integrate the SEAM for visual grounding and tracking, and the SHAS for audio segmentation, where the messages are passing from LLM to decoders through structured meta-response effectively. Given input multimodal information, ReIMO is able to output UIE label tokens as well as fine-grained groundings recurrently. We then design learning objectives to tune ReIMO to endow it with robust MUIE and cross-modal grounding capabilities. First, we repurpose existing textual UIE annotation into instruction format and use it to tune the backbone LLM for activating the UIE ability. Then, we perform both coarse-grained instance level and fine-grained grounding-aware cross-modal alignment learning, enhancing the ReIMO's capability in fine-grained multimodal semantic understanding. Furthermore, we instruction tune ReIMO on a specific corpus to build its working behavior of generating structured meta-response texts. response to the absence of standard evaluation data for grounded MUIE, we further introduce an evaluation benchmark where we annotate a high-quality testing set of 3,000 instances covering NEAR, RE, and EE tasks under 9 common modality combinations. The data further advances by annotating both modality shared specific content to simulate aligned and misaligned modality scenarios. The table here summarizes the raw sources of the grounded MUI test data. Items in the light yellow background mean they are the data after pre-processing, i.e., via modality translation, where the colored postfix means the target modality. Before annotation, we carefully select 200 instances from their corresponding testing sets, ensuring each instance contained as much IE information as possible. Before we begin the annotation work for grounding, we enrich the types of modality combinations. This is essential because most MIE datasets currently focus on the combination of images and text. However, we aim to simulate a variety of common modality combinations that could occur in real-world scenarios. To achieve this, we transform and pre-process existing datasets. Specifically, our approach involves cross-modal parallel translation to generate data in another modality. We measure the system performance by following most practices of end-to-end UIE. F1 of entity span with type for NER, F1 of all subject and object entities, and their relation label for RE. For EE, we consider event trigger ET F1 including both trigger and event type, and event argument F1 including both arguments with role types. With respect to the multimodal grounding part, for both image and audio segmentation, we consider the mean intersection over union, MIOU. For video segmentation, we use the average Jacquard, J. The above table presents the results of different models on our MUIE dataset under both text plus image and pure image conditions. We can observe that overall, the end-to-end approach, Mini-GPT-v2, outperforms pipeline methods. Besides, our system demonstrates a clear and consistent advantage consistently across all subtasks. In the below table, we see the performance of various models under text audio and pure audio input. In response to the absence of standard evaluation data for grounded MUIE, we further introduce an evaluation benchmark where we annotate a high-quality testing set of 3. In the MUIE context, different models may encounter both aligned shared information and misalignments between modalities. Now, we have categorized cases in the data as either modality shared or modality specific, and compared the performance of various models under these two scenarios. As seen, ReMO outperforms all baseline models in addressing challenges arising from misalignments between modalities. We further illustrate the impact of the number of entities or objects in an instance on the performance of the MUI system. It is evident that our ReMO system maintains commendable performance in extracting an increasing number of objects across T plus I plus A, T plus V scenarios, both in terms of MUIE results and fine-grained grounding, being clearly superior to baseline pipeline systems. Then we provide visualizations of case studies through which we aim to offer a more intuitive and comprehensive demonstration of our MUIE system with examples for NER, RE, and EE tasks, respectively, where ReMO yields correct answers and also gives explainable predictions. This is an example for NER. These are examples for RE and EE. Finally, we delve into our model itself and analyze the possible shortcomings for shedding light on future explorations. Via our experiments, we here summarize several error types, such as repetition of extracted content, incomplete information extraction, incorrect grounding match, error propagation, etc. Overall, we make 3 key contributions. First, to our knowledge, this is the first to propose a grounded MUIE setting, unifying all IE tasks across modalities, further with fine-grained multimodally grounded targets. Second, we introduce an MLLM for the task, ReMO. Third, we contribute a high-quality, diverse, and challenging dataset, setting an evaluation benchmark for follow-up grounded MUI research. Thank you again for your attention.